Welcome to our final session of the spring 2025 Step into STEM with Thanush Patlolla. Woohoo! Yay! All right, so before we get started into our programming, as usual, we're going to go over some of the basics about CEE, the Center of Excellence in Education. So first about CEE, it was founded in 1983 by Joanne DeGennaro and the late Admiral H.D. Rickover, who was the father of the nuclear navy and civilian uses of nuclear power. Our mission here at CEE is to nurture high school and university scholars to careers of excellence and leadership in science, technology, engineering, and mathematics, or STEM, and to encourage international collaboration between and among leaders in the global community. Here at CEE, we have 4 excellent programs, the first of which is the Research Science Institute, or RSI, which is starting in about a month. Woo! It is a highly competitive 6-week summer science and engineering program available to rising high school seniors. Juniors may also apply. RSI is the first cost-free summer science and engineering program that combines on-campus coursework in scientific theory with off-campus opportunities in science and technology research. We also have the USA Biolympiad, or USABO. USABO is the premier U.S. biology education and testing program for high school students. It provides the motivation, curricular resources, and skills training to take them beyond their classroom experience to the level of international competitiveness. Since CEE began administering the USABO in 2003, every member of the USA Biolympiad team has medaled at the IBO. Next, we have our newest of the 2 programs. So we have the Teacher Enrichment Program, or TEP. TEP provides opportunities for middle and high school teachers to connect with leading experts from industry and academia, explore cutting-edge research and development, and make meaningful professional links with direct benefits for teachers and students. Then finally, we have us here, STEM Lyceums. STEM Lyceums is a virtual club for high school students to meet once or twice a month to learn about STEM career pathways from leading field experts. Industry professionals share cutting-edge research and offer unique learning experiences like scholarships and internship opportunities for high achievers. You can learn more about our programs using the links that we are going to put in the chat, or to go directly to our website, www.cee.org. Today's speaker is Thanush Patlolla. Thanush is a senior at William G. Enloe High School in Raleigh, North Carolina, mainly interested in applied physics. Thanush is a 2024 U.S. Physics team member. In addition, he conducts computational materials physics research at Duke University, for which he won 9th place in the Regeneron Science Talent Search. Woo! Outside physics, Thanush is an avid jazz guitarist and captain of his school's Science Olympiad team. In his free time, he enjoys playing poker and reading. Thank you so much for joining us. We're going to go ahead and turn it over to you. And then I'm sure we're going to have a lot of questions. So y'all, if while he's presenting, if you've got questions, throw them into the Q&A. I'll start sorting them from there. But I think we're going to have a great session. So go ahead and take on over.
All right. Hi, everyone. It's really nice to be talking here today. So yeah, let me get right into it. Um, so thank you again for the great introduction. Just a little bit more about my background. So I'll be going next year to MIT to study electrical engineering and CS along with physics, which is what I mostly did in high school, a lot of physics related extracurriculars. So that's part of the US physics team, which was from the Physics Olympiad. So just like the Bio Olympiad run by CE, there's also a Physics Olympiad, and I made it to the team, which is the top 20 members in 2024. And yeah, I'll discuss that a little more later. Again, I also went to the Regeneron Science Talent Search, and that was for some research that I did at Duke University on computational material science. At school, I also participate in Science Bowl and Science Olympiad. And then I play jazz guitar and I founded my school's physics club. So this is basically a summary of like most of the things I did in high school. Yeah, most of the extracurriculars I did in high school. And what I wanted to do is go a little more in depth into how I got into these things, what my experience was like, and then how you could do something similar with whatever you're interested in. So starting with Olympiads, I got into Olympiads in middle school when I joined my school's math counts and started getting into the AMCs, which is the Math Olympiad. And from there, I started talking to some of my friends who told me about, oh, there's Olympiads in other subjects. So from a young age, I'd always been interested in physics. I'd just been reading books about physics. I really enjoyed, going to the library and finding like um, just books by Stephen Hawking, things like that. And so the summer before ninth grade, I started picking up some physics textbooks and working through them. And then throughout high school, I also participated in math CS Olympiads. But physics is the main thing that I participated in. So starting in ninth grade, the summer before ninth grade, I essentially got recommended just an online community on Discord by one of my friends. And in that community, like a lot of people had already posted resources for me to use. In general, I'd say that for every Olympiad, obviously I did physics, but I had friends participate in different science Olympiads. There's a general set of textbooks and practice resources, whether that's like past problems or other practice books that you can use to study for this Olympiad. So there's a set curriculum, usually dictated by the international level of the Olympiad. And there's a set of textbooks that's pretty good for studying this set curriculum. Um, and in general, if you want to find out about this, a good way is to go online, maybe find there are Discord servers for every Olympiad. So, for example, you might search up the Physics Olympiad Discord server and find that online, or ask around and see if you have any friends that are part of these communities. And yeah, you can as once you join one of these communities, it's really easy to find um, sort of the standard list of textbooks to work through. So what happened for me was starting in the summer before ninth grade, my friend had sent me an invite into one of these into a Discord server and I basically figured out what the standard textbook list was for physics, started working my way through it. And the summer before ninth grade, I got really proficient at mechanics, sort of the first part of physics, and took the first round of the USA Physics Olympiad. I unfortunately did not qualify for the second round, which is like the actual Olympiad. I was one question away, but um, that was like a really valuable experience for me. And I continued to study this standard curriculum. And through 10th grade, I continued studying. I didn't qualify again for the USA Physics Olympiad, but the summer before 11th grade and through 11th grade, I did I had finished the standard curriculum and just worked my way through a lot of past practice problems. Um, just past USA Physics Olympiad problems, past problems from Olympiads from other countries, and did quite well on the USA Physics Olympiad to be able to qualify for the 20-person US physics team. And so as part of the US physics team, I was able to go to a training camp at the University of Maryland, and the 20 of us took part in some advanced physics lectures and labs to practice for the international level of the Olympiad. And from there, the international team was selected. I was not selected to be part of the international team, but it was an extremely valuable experience. I learned a lot about physics and made some of my closest friends who I'm still in contact with today. So in general, some advice for Olympiads. I found that it's really, really hard to be good at Olympiads without choosing something you're interested in. I really love physics, and even loving physics so much, it was a hard journey to get really, really good at Olympiad style problem solving. Just sit down and work my way through problems. And I think if I wasn't as interested in physics as I am, then I wouldn't have had the motivation to continue after not being able to get a problem for after like an hour and then having to do another problem and do the same thing, for a year on end. But I'd say after choosing something you're interested in, figuring out, obsessing over like the exact pathway, like the exact books, the exact problems to study is not very efficient. In general, there isn't much difference between doing one textbook or another textbook or doing this set of handouts or a paid class versus some things you find online. All you need is a textbook, maybe a few people to ask questions to, which you can find as part of any like online community, and practice problems. And you just have to spend time doing these and make sure that you learn the entire curriculum in one way or another. I'm sorry for the vague advice, but like to be specific, for example, in physics, in general, you have mechanics, electromagnetism, thermodynamics, waves, optics, and um, like modern physics. I might have missed one category, but um, as long as you find that you've worked your way through any standard textbook covering this material and then done a lot of practice, you'll be fine as opposed to figuring out what the exact best textbook is or anything along those lines. And yeah, in general, spending lots of time doing problems that are like slightly too hard for you or like hard enough that you have to spend a lot of time thinking about them and just continuing to do as many problems as you can to build problem solving experience is the best way I've found to get good at Olympiads. In general, I think Olympiads have been really rewarding for me because they've improved my general problem solving skills. That's what, like, for example, math and CS Olympiads have made me better at problem solving. And physics Olympiads have really made me understood all the subtleties of the physics that I have to learn because Olympiad problems, especially the first round of the USA Physics Olympiad, the F equals MA, really tests your understanding of the edge cases of physics. Like I'll mention later, I think that participating in Olympiads gave me a really good foundation in physics that allowed me to transfer those skills to many other areas. So whether it be other competitions like Science Olympiad and Science Bowl, or into my research, albeit slightly indirectly, getting really good at Olympiads was, for me, a really good way to um, create a good foundational knowledge in physics. I think for other people, other friends I have that do Olympiads, they agree with this sentiment. But I also know plenty of people that didn't do Olympiads at all and have done very well in research or other fields. So if you feel like you enjoy the entirety of a subject enough to want to gain a really good base knowledge of it, Olympiads are a really great place to start. But yeah, there's many ways, obviously, to learn about subjects like physics. So now, moving on to research. So I started working at Duke as part of the Ames lab, that's ab initio material simulations, in 10th grade. So late in 10th grade, I sent out maybe 10 cold emails, and I was prepared to send very many more. I think I got very lucky just talking to friends. Yeah, about the 10th cold email I sent, I got a response from a professor who was willing to meet with me and discuss my level of expertise and see if perhaps there was a project that I could work on. And so we met, and I sort of demonstrated that I knew what I was talking about, at least to the extent that a high schooler can. And he proposed a project, and we started working. So the way that I was able to first build the background to be able to do research was sort of actually out of curiosity. So starting in ninth grade and early 10th grade, I had just come across some lectures online about quantum mechanics and started watching them, um, sort of out of boredom, I would say, which can sound incredible or sound like a lie, but really I was avoiding doing other schoolwork and I ended up watching quantum mechanics lectures. And so um, that allowed me to like build a good baseline knowledge about stuff beyond the Olympiad curriculum because quantum mechanics is not in the Olympiad curriculum. Just watching those lectures and doing problems allowed me to understand the material to the point where I was able to look at past research that high schoolers did, for example. I was looking at past STS and ISEF projects, which, if you don't know, are two different research competitions, to see what people working my age, working in physics, were working on. And I came across the idea of density functional theory, or DFT. I'll go over what my research is actually about on the next slide, but it's essentially computational material science. So using computer simulations to solve for materials properties. And I thought it was really interesting how I was able to understand that with the quantum mechanics background that I built just watching lectures, which is why I decided to cold email for research. So some specific cold email advice. I say on the slides you can find scripts online, but in general, my advice would be email professors being both brief and specific. So what does that mean? One, they're very busy people, especially after working under a professor who's a principal investigator for a lab. You will realize that their calendar is packed with meetings. They are always traveling, and it is extremely easy for them to click on a long email and immediately click off it and completely forget about it. You want your email to be scannable in like 30 seconds so that you can get a quick reply. And but you also want to demonstrate that, you may be mass emailing, you probably will have to mass email, but you want to put in effort. So, for example, you might go online to the professor's website, read a few of their papers or read some titles and abstracts. And even if you don't understand much, whatever you do understand, you might say, "Oh, I thought this specific aspect of your research was really interesting. I have this background, and I really want to learn more. Is there any way I can work under you?" So you can either ask to work on a project that they propose, a project that they have for you, which is a bit harder because whatever professor you're talking to needs to have a project ready for you, or you can propose a project of your own. I asked to work on a project that the professor I was working under came up with for me, but I know people that have had great success asking for help with their own independent projects. Yeah, so as part of my research process, I came in thinking I understood a lot of the background of the research that I was working on, but I will say quickly that I will say you quickly realize that you don't know much at first because obviously you were working under a principal investigator that is working at the forefront of their field. So it'll take you quite a bit of time, especially as a high schooler, to adjust and to learn. But my advice would be to put as much effort into understanding the field that you're working on instead of just doing rote work or doing things that um, your professor tells you to do, because it'll allow you to get more progress on your own, to figure things out on your own. And it'll also show them eventually, a few years down the line, for example, if you want a recommendation letter or if you, um, want to go off on your own, that you're able to come up with ideas on your own, that you're able to test things and debug on your own. And so when I came into this lab, I'd always been taught the scientific method in school, and I knew what it was in theory, but from my Olympiad experience, thought, oh, it's no different than solving problems. I just need to sit down, figure it out, and that's the answer. And I think Olympiad problems, though, are meant to be solved within an hour or a few hours. Or if you're, say, doing a problem outside your reach, you can maybe finish it in a few days. The issue with research is it's nothing like that. When I started doing research, I didn't take notes about anything I was doing. I just tried solving the problem, implementing a solution, seeing if it worked, and moving on. And I quickly found that that would never work. And now I have a some 200-page lab document. It's just a Google Doc, but detailing all of the methods that I've tried and all of the issues that I've come across, because you'll quickly realize that research problems are being worked on by researchers for a reason. They're difficult, but they're incredibly rewarding to work on. So now I've been talking in pretty abstract terms. Let me go over a little bit of what my research is on. So, like I mentioned, my research is on density functional theory. And what that is a way to take all the electrons in a material and solve the quantum mechanical equations that govern the way that they behave. So, for example, let's say you have a semiconductor material making up a solar panel. What you might do is in your computer simulation, tell your computer, I have this grid of silicon atoms with a few germanium atoms dispersed throughout, and whatever other atoms are part of that material. And then the computer will take the electrons in whatever atoms that are supposed to exist in that material and solve the equations that govern how the electrons interact with each other and with the nuclei of the atoms. And in general, actually, chemistry is really doing this study based on empirical laws and based on experimental evidence, trying to figure out rules to see how atoms interact without solving the quantum mechanical equations. But we can solve the quantum mechanical equations and get certain more accurate results. And so we want to take that approach for material simulation when we have the computational ability. When we want to do these simulations, though, it's often extremely difficult to directly simulate the equations that govern electrons. So what we do is we do what's called the density approximation. We take this many body problem in the top right figure and turn it into an electron density. So if you may have heard of orbitals from chemistry class, how the electrons are supposedly distributed like an electron cloud. Those orbitals are actually probability distributions, which if you don't know what that means, you don't need to worry about it. We just actually kind of assume that the electrons are actually spread out like a cloud. And so we come up with what's called an electron density. And using this density, we're able to do lots of calculations that get us key electron properties such as electron energies. So what I did is I worked on a correction to this that accounts for the size of the nucleus. So um, in chemistry and in a lot of these first principles simulations, we assume that the nucleus of the atom is a point at the center of the atom, which in fairness is a very good approximation. The nucleus is so small that we can treat it as a point. But there are certain applications where the size of a nucleus actually needs to be taken into account. The fact that it's made up of many protons and neutrons that are spread out in space. So how can we go about doing this? Well, the first approach that me and my professor in conjunction came up with was using charge density data from electron scattering experiments. So looking online, we found that there was a paper that detailed the way that these protons and neutrons, the way specifically the protons were distributed throughout space. Now, this graph on the bottom left here shows basically how much charge, so what fraction of these protons is distributed at a distance away from the nucleus. So we see as we get farther from the nucleus, we get a little less charge, it goes back up, and then it drops significantly. So previous approaches to this problem didn't account for this electron scattering data, the way that this charge was actually shaped. It sort of assumed a Gaussian shape, which sort of falls off like this, and assigned a nuclear radius and did calculations with that. What we did from there is we solved for the potential energy, which is sort of the energy created by the nucleus for these electrons, that's generated by this charge density, which is the next graph over. We see the finite nuclear potential for lead-208. And what we would usually notice if you've ever taken an E&M class um, is that as we get closer and closer to r equals 0, to zero distance away from the nucleus, that this potential would actually go down to negative infinity. Instead, in this graph, it sort of levels off, and that's because of the effects of the size of the nucleus. And then when we account for these effects, we see that in the very right graph, the red line is sort of the electron density as a function of radius versus so the red line is with the finite nuclear potential, the electron density versus the radial distance, and the blue line is without the finite nuclear case. And so we see that the electron density actually levels off and is smaller than would be without the finite nuclear approximation. And this is particularly useful in cases near the nucleus, such as large element 1s electrons, which the 1s electrons are the electrons closest to the nucleus, or for what's called hyperfine coupling constants, which are the way that the spin of the nucleus, like you can really think of the nucleus spinning, couples to the spin of the electrons via magnetic fields. Now, if all of that sounded a bit technical, I'll have to apologize. I need to work on getting across quantum mechanics, but it is an interesting problem. And essentially what I found throughout the research process that makes it much more difficult than it sounds right now is that solving like generating these graphs, solving for these functions using a computer can often lead to some what's called numerical errors. So when we do these computations, we end up getting inconsistencies, just adding up the nuclear charges to get to the nuclear potentials, because of the way the numbers are stored inside computers. And so we spent a lot of time doing experimentation, trying different approaches to do this, what's called integration, to get first the potential and the basis functions. And so as part of the research process, a few of the things I learned was one, software engineering. Before this, I never worked on a large software problem. A lot of the Olympiad things I'd done were obviously with pen and paper. I had worked on computer science Olympiads, but they were very small problems. They were self-contained, one file, and now I had to learn debugging skills, how to write good, clean code for other people to work on. But outside of the computer science and more in the physical realm, as part well, first part of the research process, I learned how to eliminate where problems are coming from, try different approaches, um, look inside different texts, do literature reviews to find new ways that new sources of errors, and find a new explanation for why things are currently going wrong, and slowly eliminate possible explanations until we figure out what's going wrong in the code, fix that, and then figure out that there's another error later on, fix that, maybe go back to the start, right? So when we come back to calculating um, the charge densities of the rightmost graph, I find, oh, there's an error calculating the actual charge densities in the first graph. And so it's a very cyclical process that took 2 years to generate all of this stuff, and um, that we're still actually currently working on for um, a more complicated case that accounts for special relativity. Um, so that's like a very detailed summary of what I do in my research and a little bit of the research process. I would say overall that it was extremely rewarding to work on such a difficult problem. And in general, working on research like this, um, it'll change field to field, but I think is a very good experience that was extremely different from Olympiads. And so, yeah, I'd say if you're interested in any problem in whatever field that you're working on, which you'll only find out about by doing lots of reading, looking at other people's projects, looking at current research, and things along those lines, then it's a good idea to either reach out to a professor looking for work or with your own project. And you'll find that you learn along the way a lot of useful things. So with this research, I actually applied to the Regeneron Science Talent Search. So I had to write a paper up and fill out an application. And I got selected for the top 40 finalists for the competition. And we spent a week in Washington, D.C. at the Conrad Hotel, basically going through multiple rounds of judging. So the one of the judging rounds are panel judging, which is focused on general science knowledge. So I had to go into a room for 15 minutes, sit in front of three judges, and they would ask me questions not only about physics, not about the project in general, but about biology, about chemistry, about material science, about generally like all of science. And I had to either I had to draw on my past knowledge, draw on things that I learned, or just figure things out on the spot in order to answer those questions. I will say that my biology and less so my chemistry, but certainly my biology is less strong than my physics. But it was a really fun experience to go through that judging. And then I also in DC we went through what's called project judging. So when judges came up to ask me about my project, and I had to sort of defend my decisions in the research process, things of that nature. And alongside those two judging rounds, I spent a week with the 39 other finalists in Washington, D.C., doing a lot of cool things and basically bonding and making some of my best friends now, which was a lot of fun. So after all of that judging, I did win ninth place for this research and obviously for the panel judging, which was really a great surprise. But yeah, I would say for that, it was really that the quality of my research was possibly not, this is possibly not the most impactful research, but I find that I was really careful about my research process, and I was really careful about making sure that I understood the details behind my project so that I understood the quantum mechanics behind why um, the methods that I was working on worked. And basically showing my professor in addition that I was able to understand what was going on. I was able to come up with ideas for myself and yeah, do research on my own. Um, yeah, I would also say that I came up with some of the ideas related to this on my own. So um, some of the applications of hyperfine coupling constants, things of that nature, were things that um, I was interested in applying DFT to quantum computing, and therefore um, sort of did a lot of independent research related to finding that application. I read a lot of papers and I read a lot of textbooks, which gave me a lot of understanding about higher physics in general, so physics beyond the Olympiad curriculum. And I think it is certainly possible, although more difficult, to do research on your own. But if you do decide to take that route, to be careful about making sure you're extremely methodical with your research process, that you do very good testing, not just coming up with a cool idea, but making sure um, that you test the idea very well. But yeah, my best advice would be to find a professor to work under because they will hold you through. They will take you step by step through that research process much better than any advice that I can give within an hour. Okay, and then for Science Olympiad, I started Science Olympiad in sixth grade really, but got onto the team in seventh grade. And this is actually what got me a lot into STEM competitions in general. This is really the first STEM competition that I did. And um, Science Olympiad compared to Olympiads. Um, I guess I should address that first. Science Olympiad is a bit of a misnomer compared to the other Olympiads that are focused on specific subjects. This is Science Olympiad is a team competition. You work with partners on specific events and have a larger team of 15 people that you compete together with. And it only goes into the national level as opposed to, for example, Physics Olympiad, Biology Olympiad, Chemistry Olympiad, which are all focused on a specific subject, are individual competitions, and go to the international level. But Science Olympiad got me into STEM competitions, and the specific events that I did were typically focused on physics. I also did a few building related events, which was never my forte, but which I thought were a lot of fun. I would say Science Olympiad allowed me to dive into, for example, in middle school, I did circuit lab, which allowed me to get really good at understanding circuits in specific instead of physics as a whole. As another example, I did optics this year and the previous year, which allowed me to really like hone in on that. I'd say, like I mentioned earlier, that doing Physics Olympiad gave me a lot of fundamental skills that allowed me to transfer over here. So my background in circuits really transferred over when I had to do wind power or Wi-Fi lab in high school. But I had to go um, deeper beyond my base background knowledge from Olympiad to really excel in my Science Olympiad events. Similarly for optics, I learned about the basics of optics for the Physics Olympiad, but I had to get a lot more in depth into the specific topics that were in the Science Olympiad rules in order to do well in competition. And so, some advice I have for Science Olympiad is it's again a team competition. So, obviously, being part of a good team helps. I think that I've learned a lot from my partners and um, sort of the alumni, the people that were older than me when I was a freshman in Science Olympiad. As for studying, I found that the Science Olympiad wiki and also just Wikipedia, searching up the rules on so Science Olympiad releases a list of rules for each event, and searching up the topics in those rules on Wikipedia and looking through past tests for types of questions that you have to learn was the primary way that I studied. I think it's also helpful for certain events to find a standard textbook on the event, which you can do online just by searching up stuff or by asking around. And yeah, I'd say that for me in particular, the Science Olympiad was sort of just another way for me to apply the fundamental skills that I built doing physics. Um, what I found Science Olympiad much more valuable for was sort of the community, the team bonding, and also in my later years, the past 2 years, I've been a captain of my school Science Olympiad team, which has taught me a lot about like leading a team and organizing our school's team, making sure that we're able to travel to our competitions, that we're able to organize our tryouts and do things like that, which I think has taught me some valuable things beyond STEM. And moving on to Science Bowl is also a lot of similar things. So Science Bowl is a 5-person buzzer-based competition where you have to buzz in to answer science questions as fast as possible. So I started this in ninth grade, and again, I found that a lot of my skills from Olympiad transferred over. A lot of the studying that I had to do was the same exact material. I found that obviously Science Bowl required a lot of speed skills, so we would do weekly practices to work on our speed, work on Science Bowl related skills. But again, that I found a really good community as part of Science Bowl, that allowed me to um, I have another way to display my physics ability, and that I was able to like learn leadership from the school club and from organizing the team. So, in general, the way that I approach things in high school has there's really a common theme of starting with Olympiad, which is just what I knew starting in middle school and early high school, building a good foundation and using that to jump into other opportunities. So outside of sort of well, I guess another STEM EC is our school's physics club. This was a smaller EC that I did. At our school, it didn't really take off that big, but I found that it was really helpful to write physics handouts about getting into like competition-based physics, the basics of mechanics. And I also taught a physics class. I forgot to put this on the slides. I taught a introductory physics class for the first round of the Physics Olympiad this year, which was also really valuable. It allowed me to not just learn physics, but be able to teach it to other people, which I thought was not only a good skill to learn, but really rewarding to be able to give back to the people that were once in my shoes. Um, and then yeah, outside of STEM, one of the big things that I do is jazz guitar. Um, I know this is a STEM thing, so I'll just touch on it briefly. I just joined a band to play that stuff. I think that obviously STEM is very fun, but it's um the I guess I'll put it like this. The STEM is very fun, but the general theme with my extracurriculars were that I did things that I enjoyed, which physics is a really big thing I enjoy. So I just found lots of ways to do physics in high school. But jazz guitar is just another thing that I really enjoyed doing. And the general theme with my ECs was not, what will look, well, I suppose I did do things that will look good on my resume, right? But it wasn't that I was forcing myself to do things just because they would look good on my resume. More so that I really enjoyed learning about physics. I really enjoyed doing research and I really enjoyed playing guitar. And I thought, how can I do something with these skills so that I can put it on my resume instead of just having to go around telling people, yeah, I'm really good at physics. Please trust me. Um, so yeah, that's sort of my final advice. I was really specific to the things that I did, but there are a lot of possibilities for STEM extracurriculars in high school. I just put a few things on here last minute that I know my friends have mentioned. I have a lot of friends that went to ISEF, a lot of friends actually that went to RSI, which is obviously a CE program. But the best way to learn about these opportunities, in my experience, is to talk about this with people, which obviously might not be the easiest thing to do at your school if there isn't a strong STEM community. But there's always people online, there's always people looking to uh, discuss opportunities like this. So whatever you're interested in, just try to find out places to apply those skills. So yeah, again, the my final piece of advice would be your extracurriculars don't feel like work if you truly love what you're learning. Obviously, this isn't always true. Everything will feel like work eventually, but it'll make you want to keep working when you feel really tired. Yeah.
Awesome. Thanks so much. Love that final takeaway, do what you love and love what you do. Definitely some good advice. We're gonna go ahead and move on to the question portion. I know I have a ton of questions, and then there's also questions coming in as we speak. So we're gonna go ahead and dive in. So first question, Priya's asking, how do you find an online community for Physics Olympiad? And do you need to get an invitation, for that type of thing, or can you just join?
Um, okay. Actually, I should check how easy it is to join. I know that um so the way that I found it was just that my friends invited me, but I think if you search up Physics Olympiad Discord server online, you will find it. Uh, this is yeah, just search it up. Um, like so the for Olympiads specifically, I know that there is a Discord server, which I know Discord can have a bad reputation, but it's typically where a lot of STEM things are hosted, but for high schoolers, like by high schoolers. So Yeah, just search up for Physics Olympiad Discord server, and then insert whatever other like subject you want. So chemistry Olympiad, biology Olympiad. Um, I think that they're all public. So if you search it up, you can just join it. Um, I would say that's the best way to join. Or not the best way to join. Like that's the easiest way to just find people online or find resources. If you join any of those communities, there will generally be a place like just a list of resources somewhere. And then well, obviously a lot of people to ask questions.
There's also a lot of subreddits out there too. So if you go on Reddit,
Mhm.
there's a lot of like facts and lists that they post there. So that's another great resource.
Mhm.
All right, another question is what is the best, in your opinion, textbook for Physics Olympiad?
This is okay. So I spent a lot of time in my slides, not my slides, but when I was talking, I spent a lot of time saying you shouldn't obsess over what the best physics textbook is. And this is coming from experience because I spent probably like 30 hours like Googling and asking people, oh, what's the best first textbook? Oh, I'll provide recommendations at the end, so don't worry. But yeah, I'd say like it's much more important to just pick up something and start working on it than it is to um yeah, to spend time comparing books. The standard book for physics Olympiads is Halliday, Resnick, and Crane. Should I put this in the chat or something? Um, oh, so the reason that I said to join the Physics Olympiad Discord server is because they will have like a big message with a full list, which is really the easiest way to get the full list of textbooks. But Halliday, Resnick, and Crane fifth edition is the standard book, and I mentioned like I never fully worked through this book because I didn't like it that much. But this is just my opinion. Like I'm in the like mi minority opinion for this. So you should definitely look at the book first. I know like many people who love it. And then after this book, it gets you have a few options. So actually I don't know how I gave an entire lecture without mentioning Kevin. Um So Kevin Zhou makes a lot of Physics Olympiad related advice and handouts. So let me just put his link in the chat. But yeah, that's a very good resource. So Kevin has a lot of handouts on Physics Olympiad. So after you've worked through Halliday, Resnick, and Crane, um, you can go directly to his handouts. His handouts will also mention at the top of every handout some background reading you can do. So what I did personally was I worked through David Morin's Introduction to Classical Mechanics and Purcell and Morin's Electricity and Magnetism. I think it's like the third edition. And then I believe those are the only textbooks that I worked through like cover to cover. And then I worked through some of Kevin's handouts, learned things here and there from random lectures and random problems. So, like I said, it's not too important to stress over this stuff. If you want, you can, if you want a full list of for every single subject, you look online. I know that there's an AOPS blog post about this. If you search for it, you'll find it. You can look in the Physics Olympiad Discord server on Kevin's website, or again, there's probably Reddit posts about this.
Awesome. We had another question come in. It says, how did you learn your physics knowledge in the beginning? I think you mentioned about like starting before even getting into high school. I think here in Virginia, physics is a junior level class. So like, how
Mhm.
did you get started even prior to that?
Okay, yeah, I guess um so before I like before the summer before ninth grade is when I actually started learning physics. Before that was I had what's called like pop science knowledge of physics. So um I read books in like the adult section of the library, but none of those books have any math in them, and none of those books actually teach you physics. They just make you think like, oh wow, black holes are really cool. Um so like I read like A Brief History of Time by Stephen Hawking, which made me really want to learn more physics, but it didn't really teach me any physics of substance because none of those books have any math. But as to how I was able to learn even starting the summer before ninth grade, I guess I was privileged in the fact that um, Okay, slightly privileged, but also slightly my own plan. In sort of fifth and sixth grade, I realized that I couldn't learn physics properly until I learned calculus. And so, sort of throughout middle school, I spent a lot of time learning math. And the summer before ninth grade is when I learned calculus very quickly in order to learn physics. And that can sound very daunting. I'm aware. Um, there's a few things I want to say is that uh, learning calculus for physics does not require being able to, like, to be at the level to get a 5 on AP Calculus BC. It requires just really basic knowledge of differentiation and integration. And obviously, as you get into more and more advanced physics, it's useful to know more and more advanced math. But just to get started, it's really useful to understand the very, very basics of calculus, which doesn't actually require that much background in math. So you can sort of watch a few Khan Academy videos, which is what I did, or even open the beginning of Halliday, Resnick, and Crane and just see what you don't know and Google it. Um, and that'll give you the math background. You can sort of build that alongside your physics background. But yeah, for me, I spent a lot of time honing my math in middle school, which allowed me to learn calculus and then learn physics.
Building on what you're saying, especially, about going through all these different high-level texts, do you have any study strategies that you would recommend or things that happened to work for you when you were getting ready for competition or just getting into these books?
I would say for physics specifically, it's a lot more forgiving than say like I have friends that do biology and chemistry that have much more sophisticated note-taking strategies. For physics, there's actually very little content that you need to remember compared to experience that you need. So what I would do is I would just read a chapter and then spend time doing the problems. Um, and by the time I'd worked through all the problems, whatever content was needed in the chapter was something that I basically had fully memorized. And there was always a few formulas that I didn't have memorized. I would look at them like maybe 10 minutes before a competition to memorize them. So I was never too worried about content. In physics specifically, there isn't that much content to remember. This is like very not applicable to biology. I know that it's sort of the opposite in biology Olympiad. But some strategies that I found worked for me was not while I was reading, but actually after every problem I did, I would write down what the key insight that was preventing me from getting the problem was. So obviously, if you're doing really easy problems, there's not going to be key insight. So you should probably stop doing those problems. Um, do problems that are hard that make you think, and that maybe you won't get the problem by then. Maybe you have to line by line look at the solution, right? So what I like to do was do a hard problem and if I didn't understand it, if I eventually got after a lot of thinking, I would write down what the key insight was that allowed me to get it. If I didn't get it, I'd look at the first line of the solution and then keep thinking, and then the second line and so on. And then when I got to the key line that really changed like my thinking about the problem that allowed me to get the rest of the solution, I would write that down in my notebook. And then um I told myself that I would look at the notebook before every competition I did. I never looked at that notebook, but I still think it was important to um, sort of get in the mindset of thinking about um, not every problem being completely separate, but every problem having key insights that are transferable to other problems.
Awesome. We had another question come into the chat. Let's see. If you have any, what are your recommendations when looking into possible internships at a high school level in the STEM industry? Specifically for this person, they are into aerospace because it's a little challenging to stumble upon an opportunity.
Yeah, I personally don't have any experience with this. When I was looking for research, I just looked at colleges near me. Um, I know that I have friends now that just make a lot of connections on LinkedIn, or look into competitions and then continue to talk to people from there. But yeah, I personally don't have any experience with that.
I think can you speak a bit towards like how you did cold calling to the professors? One thing I was wondering was can you expand a little bit about like how you sort of curated your tone when emailing these professors? Um, my point is that not to call out anybody, but we've had a few speakers here where people will just ask in the Q&A, "Will you be my mentor?" So, can you speak a little bit about wording and that kind of finesse there?
Yeah, I would say you like speaking specifically to like, will you be my mentor? Um, it's like imagine that like an elementary schooler asked you like just came up to you and asked you like teach me math. Like um, professors are extremely busy people, and I think if you keep that in your mind while you're writing your email, that you will do a lot better. So they're not obligated in any way to help you. They're in fact not obligated in any way to help undergraduates from their own college with mentorship. So what you want to be is polite, and you also want to make it seem like you have some value to add. So not that you are really desperate for like like an opportunity for your resume, but more so that you want to learn, you're willing to put in work, that you already have a background that is applicable to the work you want to work on. Um, and that basically eventually that you would do good research under them that would also be valuable to them.
Well, can you, so you talked a lot about your extracurriculars and how they happen to be really good for your resume, not intentionally, but
Mhm.
they did help. One of our viewers is wondering, if I take a research course from an Ivy, say, in high school, instead of doing an extracurricular like Olympiads, will it be weighted in equal importance, or will it look good on my resume, essentially?
So wait, what is the a research?
Basically, if I focus on research instead of competition, do you think that it will look good in terms of like application for college?
The first thing I'd like to say is I'm not an admissions officer. Um, but just like anecdotally, I have had many friends that focus on research that have done very well. So, um, as long as you like put a lot of work into it and you can show that like you're good at what you do, I would say yeah.
The diversity of interests is very helpful. I'll point that out, friends. Diversity and just doing the things that you are passionate about. Let's see. Anya's asking, how many practice questions would you drill and how much practice did you do per day during high school? So kind of what was the timing for your study?
Um, I think it changed year by year. I did a lot. The summer before ninth grade, I was putting in um like 6 hours a day. But okay, this was 6 hours a day on like three questions or like four questions. So I was I was doing problems that were way out of my range difficulty wise and just asking um a bunch of people like online like questions about it and bugging them. So yeah, I spent a lot of time thinking about really hard problems, but not that many problems. Through ninth and 10th grade, I didn't put in as much time. I did put in time. I worked my way through a few textbooks, but during 11th grade, um, I would say on a weekly basis, I probably put in like 20 hours pretty consistently. I don't know how many problems this translate. This translates to far fewer problems than you're expecting. I'll say that. Because you will spend maybe an hour on a problem sometimes, or um, maybe 30 minutes, 45 minutes, depending on the problem, and maybe a few hours. Maybe you spend an hour and you have to take a break. But yeah, doing problems that are beyond your difficulty range is good. And yeah, I just continued to do problems until I felt like fluent, I would say, in the type of subject that I was working on. Um, and once you reach fluency, you'll feel it. So yeah, it's like it's hard to say. I'd say 20 hours or maybe a little more was what I put in a week in high school in 11th grade.
We call that the zone of proximal development, making doing questions that are just hard enough so that you're
Mhm.
you're learning. Let's see. Another question that came in is, what was your experience with Fyodor? Did you learn from him?
Fyodor Yevtushenko. Um, who asked this question? I um I didn't go to physics camp with Fyodor. So he was not in last year's physics camp. He was there 2 years ago and this year, neither of which I was at. But I met Fyodor at MIT this year at visiting. Yeah, I talked to him a few times. I didn't learn that much from him because we didn't interact that much, but yeah, he's cool.
Let's see. How much CS programming did you have to learn? Let's see. What level was good for physics, chem, math, or a non-CS STEM? So basically, what foundationals would probably be good?
I would say that I like started learning out of interest in CS Olympiad. So um I'm currently like Yusuko Silver, which is not incredibly good, but like I have a very like decent foundation. It's like it's hard to say because for um a lot of the physics, like for part of my research, I sort of learned as I went. Yeah, learned as I went. I would say that I didn't have to use any hard algorithms in my physics research. It was like if you have CS experiences, like very like O of n, like O of n cubed, just like really, really basic for loops, while loops, if statements. But a lot of the difficulty came in understanding the math behind it, and implementing like the correct math algorithm instead of like difficult CS algorithms. I would say if you have no CS experience right now, um, well, I personally found that studying for USACO, the Computing Olympiad, was really rewarding. So if you're interested in that at all, I would say maybe just like learn for the bronze level of that. Um, it's fun to learn algorithms, in my opinion. But if you're interested specifically for application to physics or chem or other subjects, I'd say learn the basics of Python and then um, just learn as you go. Should pick up an interesting problem in your field and learn as you go.
Awesome. Let's see. How did you manage your workload between Olympiads, research, ACTs, or SATs, AP exams, how many, and your school requirements, especially in 10th and 11th grade? So, how did you find that balance?
Um, I would say what helped me a lot was that like I mentioned before, that Olympiads, those skills sort of transferred over. Like I mentioned that I'd been studying for Olympiad since the start of ninth grade, but I didn't make it to the USA Physics Olympiad in ninth grade or in 10th grade. So I think for me, which may be atypical for many people, I felt like high school was just spending a lot of time learning and maybe not that much time every single day, but just putting in hours consistently until I had enough background to the point where, before Science Olympiad competition, I didn't have to pull a 30-hour week to be able to get all the information down because I'd learned a lot of that stuff previously. Um, it's a hard question to say, like, how did you balance your workload? Because the way I didn't really balance anything. I just kept working until the work was done. So um, I'm sorry that I don't have a better answer. Um, I I'm not a good example to look at for like productivity or a calendar or a Notion or anything like that. Um,
Can I add in to say, would you think that jazz guitar was a good like break from it all, or a good kind of change of pace?
Change of pace definitely. Um, After you don't have much sleep in 11th grade, it feels like more work, but um, it was definitely a lot of fun. Like looking back, I'm glad that I did that in addition to everything else. Um, but yeah, I think like the way that I approached things in high school was building really good foundational skills, which allowed me, like learning math in middle school, doing a lot of physics made me do math, which means I didn't have to study particularly hard for the SAT math section, for example.
Mhm.
Um, or like things along things along those lines.
Because you built that fluency early
Mhm.
on. Okay, awesome. So I think we got time for maybe one or two more questions. One of them is mainly about broadly, can you expand more about what it was like getting involved with Regeneron? Like, what was that process like? And, was there anything that surprised you about Regeneron?
Um, let's see, for STS, I would say I did do science fair once, but I never like made it very far. It was very different than science fair because STS I had to write a paper and then answer a bunch of questions about my project in an online portal, upload my Common App essay and then one other like personal essay, and just a few more questions related to STEM, like my involvement in STEM. And then it was a few recommendation letters from my teachers and particularly from my research mentor, helped a ton. Well, obviously I don't know this, right? I have no insight on the admissions process, but I know that my the professor I worked under knows my capabilities really well. And so I didn't ever have to actually present to anyone. And also the people reading my project, so reading the paper that I wrote and the entire application, I actually got to meet them while I was in Washington, D.C. for judging. And they were all people that knew my field really well. They were people that had worked in density functional theory. They were people that had read the foundational papers of the field I was working on, which can often differ from science fairs, which even if they have people that are very knowledgeable in a related field, they might not know exactly what you're working on. It was not like that at all. So for STS, I really just took the science that I did um, and put it into a paper and submitted it. And I mean, I guess I don't know if the question's about, yeah, what are judges looking for? Um, I have no clue for science fair. I'm not the person asked for science fair. For STS, what I found is that all the people I talked to just had really good methodology, in the sense that even if their project wasn't really, really high impact, for STS, they had done really, really solid science. They made sure to um, like check the background on all the methods they used, done really, really good testing of all their results, like really good data analysis, made sure they um, sort of checked the results to see if it was this varies field to field, so I'm being very generic here, but sort of rewards doing good science and understanding your field really well.
So you mentioned you having to write a paper. Can you talk about like how long that paper is and like how long it takes to write the paper?
Um, so this is so slightly irresponsible of me, but I didn't spend nearly as much time on my paper as I should have. Um, I think my paper was it was a few pages long, but it was not in the it was typeset much smaller than usually it is for STS.
Hmm.
So yeah, I would say a few pages of like 12 point double column work. Um, and then uh yeah, I probably spent like 30 hours writing the paper. Um, yeah, I'd say writing a paper was an interesting experience. By that point, I'd read a lot of papers, so I sort of had an idea of what to be doing. I pulled up some papers that I thought were written well, tried to write in a similar style, go section by section. Um, but I knew my research really, really well, and so I found that I didn't really struggle with writing the paper because I was just writing my thoughts about my research in a way.
Yeah, I think that's one of the big takeaways is like you have to know your stuff in order to even make it to make
Mhm.
it as far as you did. Let's see. I think we got time for like one more question. Let's see. Sunil's asking how many APs did you take and if you took any APs, IBs maybe. Um, and I would want to add on to, which one did you find the most compelling or useful or helpful?
Um, I don't remember. I don't want to sit here and count and waste people's time. It's probably like 10-ish. I took two dual enrollment classes at a local community college and like six dual enrollment classes at a local state school, and a few IB classes as well. Um, and then yeah, like probably like 10 APs. Um, Maybe somewhat surprisingly, I found that my two most compelling APs were AP US History and AP Literature. Probably because those were the classes that I learned the most in. Um, I'd already learned a lot of physics before I took AP Physics, and so I found that I wasn't really learning that much in that class. Um, but yeah, AP US History and AP Literature gave me um, a better appreciation for the humanities. So um, I'm really glad that I got exposed to stuff outside of STEM, and now I have a much greater appreciation for that stuff.
Awesome. Thanks so much, Thanush. That was great. We have a few questions that we haven't gotten to, but I think we'll go ahead and I'll pass them along in our email. Um, and we're going to go into the closeout of our session. So thanks again, everybody that has been here with us. Thanks, Thanush, for joining us. This was an excellent talk, excellent discussion, and I think we have a lot of great resources to take away from it. Um, Again, we'd like to thank our sponsors for our content, especially the Claude Moore Charitable Foundation. They are what makes this all cost-free to you all and keeps providing our services. So thank you again to our sponsors, thank you to our speaker, and thank you to the students. Shout out to any 12th graders that are here and that may be graduating out of Lyceums this year. I'll miss you. If you still come, even though you're in college, that's okay. I won't tell anybody. Um, Again, like I mentioned before earlier in the session, please complete the post-webinar survey. Please complete the end of year survey. Those are things that help us develop great programming for you all, and it does your attendance so that I can offer up more opportunities for you, like the mentorship program. So these are some QR code links for our survey. I can also drop the original link back into the chat again so that you all have it and you can do them. That would be wonderful. We are going to be taking a break in STEM Lyceum's programming for a month, and we will be back in action on August 6th. We are going to be doing a session on nuclear engineering on August 6th, and then another episode on research pathways on the 13th. So we're ready, locked and loaded, and ready for the fall. Thank you, everybody, for joining us. It was great.